In this video, we're going to talk about hybridization as it pertains to bonding and molecular geometries. So the molecule we're going to start with our focus on is methane, CH4, one of the more simple organic molecules, and it has a tetrahedral geometry, both electron and molecular geometry. Now, if we drew the electron configuration for our orbital diagram for carbon, we would see that it has 6 electrons, so it has 2 in the 1s subshell, 2s2, 2p2. And this wouldn't accommodate for this type of bonding. When we draw the Lewis structure, we draw carbon with 4 dots around it. Now, it wants to form 4 bonds for a couple of reasons, but one of which is to establish the octet rule, or fulfill the octet rule, and complete its outer shell. And in order to do that, it has to go from a situation where it has an s orbital and 3 p orbitals, where the s orbital has a spherical shape, and then there's a p orbital which has 2 lobes on each of the 3 axes, and it will hybridize to the point where those 4 orbitals blend together to make 4 sp3 orbitals. Okay, so now these orbitals are equal in energy, and they can each be populated by 1 electron, and that allows for it to form the 4 bonds that we see in methane. Now, it's not entirely based on electron configuration, but it's based on how the electrons will spread out according to Vesper theory, because the valence shell electron pairs will repel each other. So when we get the shape for methane, we have the 4 sp3 orbitals, which are hybridized, and they spread out as far as possible, about 109.5 degrees, and that's a tetrahedral electron geometry. And because there's no unshared pairs on the carbon, it's also a tetrahedral electron geometry. Now, if we look at ammonia, ammonia is NH3. So we have the nitrogen and the 3 hydrogen atoms, and while it still will hybridize in the same way because there's 4 electron domains and they're going to want to spread out as far as possible, and if they're going to be essentially evenly spread out, they kind of have to be of the same energy, and you end up again with 4 sp3 orbitals. So it's completely hybridized to sp3, even though one of the orbitals only contains electrons that come from the nitrogen in the form of the unshared pair. But that's why you get similar bond angles of just under 108 for the ammonia as you do for the methane. Again, 4 sp3 hybridized orbitals in this case, because there's 4 electron domains. If we come over here, we're going to take a look at water, which is a bent structure, but it's a tetrahedral electron geometry. It has 4 electron domains, so again, they're going to spread out approximately 109.5 degrees. This is going to be smooshed a little closer together to about 104.5, but it's the same idea, in that the orbitals, the valence orbitals, are going to spread out, essentially forming 4 sp3 orbitals. Now, all of these bonds are what we call sigma bonds. So these 3 molecules all have tetrahedral electron geometries, and they all have sp3 hybridization. But that's not always what happens. These all contain only sigma bonds, which is the first connection between atoms, and it's going to be direct, where the electrons are shared directly between the nuclei of the bonding pair. Okay, and it's also going to be, they're going to be called sigma bonds. They're the first connection, and they're between hybridized orbitals. But bonding doesn't always happen between hybridized orbitals. If we take the case of formaldehyde, which is CH2O, if you drew its Lewis structure, it would look like this. And you can see that there's only 3 electron domains, and that means that there's going to be 3 hybridized orbitals, but there's also going to be an unhybridized orbital. And if we zoom in a little closer to what that would look like, you have a sigma bond that forms between the carbon and the 2 hydrogens, as well as that first connection between the carbon and the oxygen. And so since these 3 are spreading out to be essentially equal in energy and equal in distribution, you're going to have 3 sp2 hybridized orbitals. But that 4th orbital in its valence shell, that p orbital, it's not spread out evenly with the other ones. It kind of is in its original p orbital shape, and so it remains unhybridized. And this, we call this connection that happens because it can't fit the electrons directly between the atoms. It essentially goes around that sigma bond and forms what we call a pi bond. So a pi bond is between unhybridized orbitals, and pi bonds are unique because they allow for resonance and they allow for pi electron interactions and lead to some of the dynamic properties of molecules that we see in organic chemistry.